Hello everyone, this is a quick demonstration trying to be interactive here about filters. So as we have seen in the class, or if you're watching this without going to the lecture, or before even the lecture, well done, we are going to see filters in some stage of this module, or we have seen already. Here I have a voltage source, an alternate voltage source. To do this, I just right click here, edit, and put AC. I have a 100 ohms resistor, and I have a 1 microfarad capacitor. And by just looking here, we see that for a low pass filter, a first order just like this, we have our pass band, and up until the point we reach a frequency in which the value of the amplitude here is half of the amplitude that we had before. This is in power, right, not voltage. And then from this point onwards, the output power is basically decreasing with a slope of minus 20 dB per decade. And to determine this, we have a simple formula. You can see here, it's 1 over 2 pi RC, or you can have this with an inductor as well, but with the capacitor is the most common one. Capacitors are very cheap and easy to find, so we tend to work with them a lot more than the inductors. And let's look at my faucet. So yeah, it is right here. So we have a resistance of 100 ohms, a capacitance of 1 microfarad, and we can see here that the 3 dB cutoff frequency is almost 1.6 kilohertz. And as I increase this, so 100, it's 110. Let's try to find something close to there. So when my capacitance is 16 microfarad, I should have a 3 dB cutoff frequency of around almost 100 hertz. So let's run the simulation here. All right. This has an amplitude of 1 volt. And remember, let's look at here, this probably shows us that the output voltage should be 1 over square root of 2. All right. I would have explained this to you in the lecture, so don't really worry. And yeah, so we have here our filter is a first order filter, therefore our voltage output will be VO equals to VI, V in, that in this case is 1, times 1 over square root of 2. It's about 0.707. Let's look at it now. So I'm going to put here a frequency of 100 hertz. And again, when I reach a capacitance of 16 microfarad, I should see a voltage of 0.707. That's right. So there we go, it is running. Let me stop right here and let's see the peak voltage. It's almost 1 volt. You can see here it is reaching there. Now let's bring this capacitance close to 16 microfarad. Now you can see here in green, right, not the yellow one, in green, that at 16 microfarad, my voltage is about 7.08. So again, it's not exactly there, as you can see here. So if can I just remove plot properties? Show current, yeah, that is much better. So if I reset, bring my capacitance here back to 1. So right now we only see the voltage, and let me run this here. Let's see if it's going to scale. It doesn't scale. Can I scale, max scale? There we go. So right now we are reaching very close. You can see here the max is 0.998 volts. Let's increase this guy close to 16 and 15.9, good enough. Now let's run this here to see what is this new maximum voltage. Here we have 780 millivolts. There we go. So you see here, this works very well. If I keep increasing my frequency here, as you can see, you should only see this decrease more and 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 more until it gets to a point that is very, very small. Let's increase this here. So now you can see that the maximum voltage is about 196 millivolts. And if I keep increasing my frequency until forever, you should see 0 volts. The reason for this is, remember, voltage is the voltage here is the voltage difference between this spot and this spot. And the formula of the impedance for this capacitance, let's see here, is 1 over 2 pi fc. As I increase the frequency, this impedance decreases. That means this number here, the ohmic value, let's call it like that, this capacitive reactance, decreases as well. So my voltage is more concentrated here on my resistor. So you can see it in here and max scale, and we can see that the voltage over the resistor is almost 1. And as I decrease my capacitance back to 1 microfarad, you see that the voltage over the resistor decreases, goes to 300 millivolts, and the capacitance goes up to 950 millivolts, because now there is a higher voltage potential over here than over here. So this is how a filter works, and as I decrease my frequency, and let me include my speed here, I have more and more voltage over my my capacitor. And if I increase my frequency, this voltage goes into my resistor. And if I keep doing this, you can see here, this kind of, I'm modulating the amplitude, which is kind of quite cool. This has application for other things. So this is a filter. If I want to see this in the real, in the frequency domain, we can look at LT spice. So let's put it at LT spice here very quickly. Voltage, a resistance, a capacitance, connect to ground, F34 wire, and here we are. Voltage advanced. This will be a sine wave, IC amplitude of 1, and here I have a resistor. So the resistor was 100, right? And the capacitance was about 16 microfarad. And we should do an AC analysis. So let's go here, AC analysis, type of switch decade, number of points per decade, let's put it 100. And start frequency, let's start at 1 Hertz. And we know that from here, at 16 and 100, our cutoff frequency is about 100 Hertz. So if I do the simulation until 1 kilohertz, we should see that dip. I'm going to simulate, it's simulated, and I want to see the voltage of this capacitor. And we see here at 0 dB, when we go very close to 100 Hertz, right here, we see I have my magnitude of minus 3 dB. That means half of the power is circulating over this capacitor, therefore to my load as well, that would be connected into here. This is it. I hope you found this video useful, and bye-bye.